Hi, today let's go on to Hamiltonian Dynamics. So the first session from Hamiltonian Dynamics will be more of an introductory nature. We'll introduce the concepts and some of the ideas, some of the formulae we'll need to solve problems, and some of the techniques, all right, or some of the steps that we'll need to solve problems later on. Okay. We'll also discuss almost all the basic concepts, including the connection between Hamiltonian and total energy, okay, which will help us to solve problems in a quicker manner, at least for some problems, most of the problems really. And we'll also have this connection between cyclic coordinates and conservation theorems that we discussed in the Lagrangian formalism. Okay. Before that, we'll be discussing the Hamilton's equations, the Hamiltonian function, etc. So in the Lagrangian formalism, we have a function, okay, which we call as L of qi dot comma t. Qi were called the generalized coordinates, and qi dot you can call them as the generalized velocities. Okay. So these are n generalized coordinates. We have got n generalized coordinates here. Okay. And we found the equations of motion. Okay, you can either find it out using the D'Alembert's principle or from the principle of Hamilton's principle. Okay, we have done these things. Hamilton's principle, okay, which is sometimes called also as the principle of least action, etc. So this equation actually tells us, it governs the evolution, the time evolution of the system. Okay, this equation governs the time evolution of the system, and constructing and solving this equation, we can find qi of t and qi dot of t, okay, which is a complete specification of the state. Right. So in order to solve this, we need two initial conditions, all right, or actually two n initial conditions. This you can think of them as constants of integration. Okay, so once we have this, or once we have the position and velocity, generalized position and generalized velocity at any time, we can just solve these equations to find the positions and velocities at any other time. Or in other words, if you know the state of the classical mechanical system at any time, by solving the Lagrange's equations, you can find the state at any other time. All right, so the state is specified by qi and qi dot. You need two n variables to specify the state completely. All right, so we have this n generalized coordinates here. We say that this n coordinates actually specifies the configuration of the system. Okay, n coordinates, or let's say generalized coordinates. Okay, it specifies the configuration of the entire system, right? The configuration of the entire system. So if you have an n-dimensional configuration space, one point on it will give you the configuration of the entire system at that particular point. Okay, so you can think of the Lagrange's equation as giving you the trajectory of the system, right, represented by let's say a system point in the configuration space. So what you get essentially is a curve in the configuration space. We can see how the configuration changes with time. Okay, all right. Now there's a next level of formalism in classical mechanics. It's known as the Hamiltonian mechanics. It was formulated by Hamilton circa 1830, okay, around 1830s. So it's basically the same thing. I mean, in the sense that you don't get any new information from the Hamiltonian formalism. Okay, it may not also be particularly simple. It may not also be simpler than the Lagrangian formalism, but this is very important. Okay, the Hamiltonian formalism is very important. It gives you a different structure, it gives you a different formalism, it gives you a different way of looking at classical mechanics. Okay, so also in the context of going from classical to quantum mechanics, this particular formalism is very important. So the basic motivation here is to make an effort to put qi and qi dot on a more symmetric footing. Okay, so in this case they are not really in a symmetric footing, all right, because we are talking only about the configuration of the system. All right, so instead of qi dot, it's convenient to work with the generalized momenta, which is defined in this way. Okay, we know this. There are n generalized momenta which are given by dou L by dou qi dot. So it is convenient to work with momenta. There are various reasons for that. One of the reasons being that the momenta is the conserved quantity associated with some sort of symmetry, for example, space translation symmetry. Okay. Now, so instead of qi dot, we'll work with pi. So essentially what we need to do is that we take the Lagrangian formalism, and instead of qi dot, we'll have a pi. Okay. So, and then will do, and what Hamilton did is to try to place Qi and Pi on an equal footing. So instead of Qi and Qi dot, we put Qi and Pi on an equal footing. Okay, and just like the Lagrangian in the Lagrange's formalism, we need to find a function, okay, on phase space that will determine the unique evolution of Qi and Pi. So we need some function which we will call as the Hamiltonian, which we are trying to find out. Okay, just like the Lagrangian determines the unique evolution along in configuration space. Okay, we need a function that determines the evolution in what we call as the phase space. Okay, what's the phase space? Phase space is the 2 n-dimensional space. Right, you have got you have got n generalized coordinates and n generalized momenta. So if you imagine 2 n-dimensional space of which each point, all right, you have got some sort of 2 n-dimensional space. Okay, I'm not actually drawing it. So each point, in order to specify each point, you need n coordinates and n momenta. Okay, so you need 2n numbers to specify a point in the in the phase space. Okay, and this point, all right, the point in phase space gives you the state of the system, Okay, we'll discuss these things. So this means that it should be a function of Qi and Pi, not of Qi dot. Very important thing you have to remember. Okay, the Hamiltonian, the function that you are talking about, should not be a function of Qi dot. It's a function of Qi and Pi. Okay, it must also contain the same information as the Lagrangian. Okay, now so the thing is that we take the Lagrangian, which determines the evolution of the system in configuration space. Okay, and we need a new function which also determines the evolution of the system. Okay, in this case in phase space, but which also determines the evolution of the system, but which depends on Pi instead of Qi dot. Right, so we need to take the Lagrangian and find another function which is a function of Qi, Pi and T. We need to change one variable. We need to switch from Qi dot to Pi. Okay, now these things are done easily using a mathematical trick known as the Legendre transformation. You might already be familiar with some kind of Legendre transformation from your experience with thermodynamics or statistical mechanics. All right, so there are certain thermodynamic potentials which we call the energy density or the entropy, the Helmholtz free energy, the Gibbs free energy, the enthalpy, etc. Okay, these are called thermodynamic potentials, and you can go from one thermodynamic potential to another one. Okay, by Legendre transformation. Okay, in each Legendre transformation we will be changing one variable. All right, for example, we might be substituting the pressure in the place of volume. Okay, that's a change. So if you have function of volume, okay, you may need to find a new function which is a function of pressure, and then you can use a Legendre transformation to do this. Okay, or we can shift between the entropy and temperature. Okay, and these sorts of things. Now there's this mathematical trick is the Legendre transformation. Okay. Now the Lagrangian is a function of coordinates, their time derivatives, and there can also be a time dependence. Okay, there can also be an explicit time dependence. Okay, now we define the Hamiltonian to be the Legendre transform of the Lagrangian with respect to Qi dot variables. All right, so we define a new function. Because we need a function of Qi, Pi and T, we say that this is given by this particular Legendre transformation. Okay, so you see here we need to substitute Qi dot by Pi. Okay, so what we do is that we make this difference. All right, we take Pi Qi dot. All right, you need to go from Qi dot to Pi, so you take Pi Qi dot minus L. All right, and it's also important that this Pi and Qi dot are related by this function. Okay, so we can easily see that this gives you a new function which depends only on the coordinates and the momenta and does not depend on Qi dot. Okay, this can easily be seen. All right, so one thing you need to do to see this is that you need to substitute. Okay, so wherever this Qi dot comes, so you see that there's a Qi dot here and there's a Qi dot here. So wherever this Qi dot comes, you need to substitute it using a Pi. Okay, so in order to do this, you need to find Qi dot as a function of, let's say, Qj, Pj and T. All right, if you know this functional dependence, wherever this Qi dot appears, you can substitute it by a function, okay, a new function. So you can write Qi dot as a function of Q, P and T and make the substitution and eliminate all the Qi dot from here. Alright. So the important relation that we need to use here is that of the conjugate momentum. We know that the conjugate momentum is given by dou L by dou Qi dot. Okay. Now if you look at this, dou L by dou Qi dot can be a function of Qj, can be a function of Qj dot, and there can also be a time sitting somewhere inside there. Okay. Now you can actually, assuming that you can invert, all right. So you invert this particular relation. Okay, you have got Pi as a function of Qi dot and T, or Qj dot and T. Now you can actually invert this to find a function Qj dot or Qi dot as a function of Q, P and T. Right. So now once you have this Q dot as a function of Q, P and T, you can substitute this Q dot in terms of Q, P and T all over in this relation, and then you get a function which depends only on Q, P and T. That's a technique. Alright. Now, is it really obvious that this is only a function of Q, P and T? If you make this transformation, is it obvious that this is only a function of Q, P and T? Right. This can easily be checked. Right. You just take the variation of the Hamiltonian, dH. Okay, the differential, the variation of the Hamiltonian. All right, and you just use the product rule. All right, so if you use the product rule here, you see that. Okay, so if you take it dH here, okay, dH, this is equal to, there's the summation over I equal to 1 to n, that has to be the, this is Pi Qi dot. All right, so if you take the variation, okay, it's a different, it's just the product rule, so it becomes dPi Qi dot plus Pi dQi dot. Alright, this is simply d of Pi Qi dot. Alright, it's just the product rule here. Okay. And then you need to find dl. What's dl? dl can be written as, using the chain rule, dou L by dou Qi dot. Okay, there has to be a summation here. I am assuming that the summation is implied, or we can write the summation explicitly. Okay, we had talked about the Einstein summation convention, so let's assume that the summation is implied because this is repeated. So you also have dou L by dou Qi dot, and this is dou L by dou Qi dQi, and dou L by dou Qi dot dQi dot, and then dou L by dou T dt. This is known as the chain rule. Alright. So these things we use here. So this is dPi Qi dot, as we said before, plus Pi dQi dot. Okay, this comes from d of Pi Qi dot. Alright. And here we have got dou L by dou Qi dQi plus dou L by dou Qi dot dQi dot plus dou L by dou T dt. Alright. So here remember that I have used the Einstein summation convention. Okay, I have used the Einstein summation convention. Alright, which means that I have not put the summation explicitly here, but you should remember that there is a whole summation sitting here. Alright, you can write one summation. There's a summation sitting here, there's a summation sitting here also. Okay. Now, what is this? This is dPi Qi dot plus Pi. What was Pi? Alright. So as I said, it's important that you should be able to write this Pi in terms of the Lagrangian. We already know that Pi is dou L by dou Qi dot. Okay, so we'll write one more step here. All right, so either you can write this Pi as dou L by dou Qi dot, or you can write this dou L by dou Qi dot as Pi. All right, now you see that this Pi dQi dot and Pi dQi dot, they just get cancelled. Am I right? They just get cancelled, and what we have left, we have got dPi Qi dot or Qi dot dPi, okay, minus dou L by dou Qi dQi, that comes from here, and then minus dou L by dou T dt. That's what we have here. Okay. Now if you look at this, okay, let me write it in a slightly more enlightening form. This is Qi dot dPi minus dou L by dou Qi dQi minus dou L by dou T dt. Alright. So you see that this dH involves the changes dPi and dQi and dt. It does not involve a term like dQi dot. All right. So from this we can say that the Hamiltonian, the function that we have constructed using this Legendre transformation, is indeed a function of q, p and t, and there is no explicit dependence on qi dot. All right. So this is what we do. Okay. Now we can obtain the Hamilton's equation by rewriting this. Okay. We can also write this dh. We know that h is a function of q, p and t. All right. So what is dh? dh is dou h by dou qi dqi, summation implied. Okay, it's just the chain rule, plus dou h by dou pi dpi, okay, plus dou h by dou t dt. All right, this is another way of writing this dh. All right, now you compare this with this. Okay, so you can look at the coefficient of dqi, you can look at the coefficient of dpi, you can look at the coefficient of dt in both expressions. All right, both these expressions correspond to dh. All right, this is dh and this is also dh. Okay, now let's look at the coefficients of dqi. Okay, there's a dqi here and there's a dqi here. Okay, so this means that you can equate them. So dou h by dou qi is dou l by dou qi with a minus sign. All right, now what is dou L by dou qi? From the Lagrange's equation we have this d by dt of dou L by dou qi dot is equal to dou L by dou qi, or dou L by dou qi is d by dt of dou L by dou qi dot. So this means that this is also equal to what's dou L by dou qi dot? It is pi. Okay, so d by dt of pi is pi dot. So you can say that dou L by dou qi dot is pi dot. Okay, so this dou L by dou qi, dou L by dou qi is pi dot. So the dou L by dou qi here is simply pi dot. Okay, dou L by dou qi is pi dot. So if you compare the coefficients, you see that dou h by dou qi is equal to minus pi dot. All right, or pi dot is equal to minus dou h by dou qi. All right. In a similar manner, if you compare the coefficients of dpi, you see that qi dot is equal to dou h by dou pi. Okay, and similarly, compare the coefficients of dt, you see that dou L by dou t is equal to minus dou h by dou t, or minus dou L by dou t is equal to dou h by dou t. All right. Now these are known as the Hamilton's equations of motion. All right. So as we expected, we have found a function using Legendre transformation which governs the time evolution of qi and pi, which governs the time evolution of the coordinates and momenta. All right. So because once you construct this, if you have the Hamiltonian, you can construct these equations and solve and obtain, of course, pi of t and qi of t. Right? So in order to solve this equation, you need n constants of integration. To solve this also, you need n constants of integration. These are first order differential equations. Okay, so just as in the Lagrangian formulation, we need 2n constants of integration, or 2n conditions. Okay, 2n boundary conditions, so to speak, to solve the problem completely. All right. So these are Hamilton's equation. Now we have got n second order differential equations. So in the place of n second order differential equations, as in the case of the Lagrange's equation. All right, the Lagrange's equations were n equations, but these are second order equations. Now we have got 2n first order differential equations separately for qi and pi. Okay, so conceptually this thing is rather useful. All right. Okay. Now just discussion to put things in perspective. So if you remember, this qi, the set qi defines an n-dimensional configuration space which we call as C. Okay, it's clear, right? Because there are n coordinates. You can imagine an n-dimensional space where each point, in order to specify each point, you need n numbers. All right, if it's a three-dimensional space, you need three numbers. We call it x, y, and z. All right, we need three numbers in three-dimensional space. So if it's an n-dimensional space, to specify each point in that space, you need n numbers. All right, and what we get from the Lagrange's equation is a time evolution in the time evolution in the configuration space. All right, so what we see is how the configuration changes. All right, initially this is the configuration. The Lagrange's equation will tell you that by solving the Lagrange's equation you can find the configuration at any other time. So you can think of the Lagrange's equation as governing the trajectory of the configuration space, or trajectory of a point in the configuration space. Okay, but in order to define the space you need qi and qi dot. All right, or qi and pi, qi and qi dot, or qi and pi. All right, so because so what do you mean by the state of the system? What do you mean by the state of the system? Okay, in a simple way, the state of the system means that this is the information you need to predict the future. Okay, predict the future, for example. This is just an example. I'm not being very accurate here. So by state, what we mean is that it's the information that you need to predict the future or the past given the dynamical equation. All right. So here the dynamical equation is the Lagrange's equation. All right. And what do you need to work with the Lagrange's equation? You need the initial position and momentum, or you need the initial position and velocity, just like in Newton's equation. All right. So the state is qi. So the state of the system is actually this set qi pi. This is the information you need to specify the system completely, specify the state of the system completely. All right. So once you have this, you can use the Lagrange's equation to determine the state at all times in the future. All right. Now this pair qi pi, you can say that it defines a point in a 2n dimensional phase space. You have a 2n dimensional phase space. So what's this 2n dimensional phase space? It's this space in which each point, in order to specify each point, you need n coordinates and n momenta, or 2n coordinates and momenta, or in general speaking, you can say that it's a 2n dimensional space. It's a 2n dimensional space. Okay. So in this case, we can say that the evolution is governed by the flow in phase space, not in configuration space, but in phase space. So if you take a single system, all right, and you define the state of the system, the position and the momentum of the system by a point in phase space. All right, so every point in phase space is a possible state of the system. Right, every point in phase space is a possible state of the physical system. Right, so all you need to determine, okay, all you need to give in advance is what's the state of the system now. All right, or at what point is the system in the phase space. All right, so suppose you say this is the point, so this is a 2n dimensional space. Okay, I'm not drawing all the 2n dimensions, but imagine this is a 2n dimensional space. Okay, so you've got a point in this 2n dimensional phase space, and this point actually defines the state of the system. All right, now once you know the state of the system at any time, all right, you can find the state of the system at any other time by solving the Hamilton's equations. All right, because this is the set qi pi, and Hamilton's equations tell you how this qi and pi change in time. All right, how they evolve in time. So after some time, it will go to a new position and momentum. So new set of position and momenta. Let's say qj and pj. All right, qj and pj, that's a new set of position and momenta. So you see that the Hamilton's equations actually gives you the trajectory of the system point in the phase space. All right, trajectory of the system point in phase space. Okay, this is a very convenient thing, and we'll be dealing with such trajectories in some of the problems later on. Okay. All right, now if you just compare the configuration space and the phase space, you see that in the configuration space, a general trajectory can be like this. All right, the configuration changes, it can come back to a different configuration, and then it can go in a different direction. Okay, this is the trajectory in configuration space. All right, but in a phase space, all right, in a phase space, this trajectory cannot intersect. The trajectory cannot intersect. All right, why is that the trajectories cannot intersect like this? Okay, this is the configuration space, and this is the phase space. Okay, the reason is that given the position and momentum at any time, right, given the position and momentum at any time, the future is completely determined by the Hamiltonian. The future is uniquely determined by the Hamiltonian. All right, so if this is the phase space, and this is the point in phase space. Okay, this is the state of the system, which is represented by a point in phase space. Okay, the Hamiltonian uniquely tells you what will be the next state, all right, or what's the next state of position and momentum. all right. So suppose it intersects, suppose the trajectory of the system in the phase space, all right, this in phase space, suppose it intersects like this. What does that mean? All right, suppose you specify the state by this point in phase space. This means that the evolution is not clear. It could go there, it could go there. All right, so the evolution is not unique. All right, so if it actually intersects in this point, then it means that there's a point in phase space, okay, at which the evolution is not unique. All right, but the Hamilton's equations are telling us that given the state of the system, the future is completely determined, or the future is completely determined. The future is uniquely determined. It's not only completely determined, but it's also uniquely determined. Given state, there's only one possible future evolution governed by the Hamiltonian. Okay, I hope this is clear. So if it's actually intersecting, this means that, okay, suppose this is intersecting like this, all right. So it's not clear if this is the state of the system. Okay, if the state of the system is given by this point, it's not clear what the future is. It's not unique, all right. But the Hamilton's equations say that it's unique. So the trajectories in phase space cannot intersect each other. Okay, so this is only true for autonomous systems. We won't be dealing with non-autonomous systems, all right. So the basic idea is that if you keep changing the rules of evolution, then of course the trajectories can actually intersect, all right. If you change the Hamiltonian in between, then of course, okay, the Hamiltonian may be time dependent, or it has changed, and then of course the evolution may also be different, all right. So this is only for, let's say, so most of the systems that we discuss, all right, if the Hamiltonian does not change in between, if you don't change the rules of the game in between, then the evolution is actually unique and the trajectories in phase space cannot intersect, all right. So it's a good thing to remember this thing, that if you see a trajectory in phase space, it cannot actually intersect, all right. It cannot go two different ways starting from a particular point, all right. So paths in phase space can never cross. So given the state of the system at any time, the past and future states are uniquely determined by equations of motion. All right. In other words, we can say that the dynamical laws in classical physics are deterministic and reversible. All right. So if this is the time evolution, it goes like this. If you know the state here, all right, if you know the state of the system, imagine this trajectory in phase space. If you know the state of the system, you also know from which state it should have come, okay, just by solving the Hamilton's equation. You also know to which system to which state it will go. You also know from which state it has come. So this means that it is deterministic, it's reversible. Okay, once you know the present, you can know the past also. That's what we mean by reversible, all right. Okay, now the rule that, okay, this is an often what do you say, not explained, all right. This rule is not explained, it's always understood, but I am stating it explicitly here. The rule that the laws of physics must be deterministic and reversible, all right. This is true for all laws of physics. If you take quantum mechanics Schrodinger equation, or if you take the equations in general theory of relativity, in fundamental physics, all equations of motion, okay, are deterministic and reversible. Okay, this is known as conservation of information. All right. Okay, so this is a general feature of all laws of physics, all right. They are all deterministic and reversible, all right. Now, so how do you find the Hamiltonian? Given the Lagrangian, how do you find the Lagrangian? All right, that's the question, okay. Normally you should follow the following steps, all right. So first you write the Lagrangian. You can do it as t minus v in most cases. Right. So if you are doing problems for an examination, maybe you can write it in most cases as t minus v, the Lagrangian as t minus v. So first you construct the Lagrangian, find the conjugate momentum. Okay, find the conjugate momentum. Now you invert this, all right. From this relation, you can find qi dot as a function of qj, pj and t. You invert this, right, because we don't want any q dots in our Hamiltonian. Now you find the Hamiltonian by this equation. It's pi qi dot minus L. We have already found this qi dot from here. Okay. Now this will be actually, if you do this alone, this will be mixed function. There can be qi sitting here. There can be qi dot and there can be pi in it. All right. Because this Lagrangian is a function of qi, qi dot and t. So once you do this, your job is not done, because now you have a mixed function of qi dot and pi. All right, but we need a unique, you don't need a mixed function, you don't need any dependence on qi dot. All right, so now the next step is, after doing this, you have to substitute all qi dot in terms of pi and qi. All right, so that's the next step. These equations, okay, these are equations 3, these are inverted to obtain qi dot as function of q, p and t. All right, and then we eliminate, so using this we eliminate all q dot from the Hamiltonian, from this h here. All right, we eliminate all q dot, it's important. All right, okay, so these are the general 5 steps to find the Hamiltonian of the system. All right, so these steps are always correct, you can always use these steps. Okay, and sometimes the Lagrangian may not be, you may not be able to write the Lagrangian as t minus v. There are cases where we can write them as t minus v. In most cases that we do, Lagrangian is always t minus v. All right, but if there are places where we cannot do that, then we start with the Lagrangian and then we can find the Hamiltonian using this rule. Okay, the rules are the same. Right? Now, but the interesting thing is that for many systems, this procedure can considerably be shortened. You don't have to go through all these steps. All right. So before going into the next thing, I want to remind you that whenever you find the Hamiltonian, you make sure that there are no q dots sitting in that function. All right. It's a common mistake that students make. We do all these steps, we write a Hamiltonian, and then there may be some q dots sitting inside. Okay, that's wrong. We need a function which does not depend on q dot. Okay. Now you can actually show that h equal to t plus v. Right? If Lagrangian is t minus v, you can simply write t plus v and get the Hamiltonian. Right? Not only should you write t plus v, you should also substitute all q dots in terms of p, in favor of p. Okay, but generally the Hamiltonian function, you can write h equal to t plus v and then find the Hamiltonian from this by making, what do you say, so this h can be a function of q dot p and t. Right, and from this we can find the Hamiltonian, which is a function of q, p and t. So there are not many steps here, we just write t plus v and then substitute, or you get rid of all the q dot, then you have got the Hamiltonian. Okay, but you cannot do this always. Okay, you cannot do this always. All right, so there are 2 rules here. You can check the textbook by Goldstein. So I have given the reference here for a detailed discussion on this. All right, so the question is, when can I write h equal to t plus v? When can I write h is equal to t plus v? Okay, there are 2 conditions that have to be satisfied. The first thing is that this transformation equations should not involve time explicitly. Okay, if the transformation equations involve, the transformation equations means the transformation equations from Cartesian to generalized coordinates. All right, it must not involve time explicitly. If it involves time, then the Hamiltonian is not t plus v. Okay, now it's also important that the forces that can be derived, all the forces appearing in the system can be derived from a conservative potential. All right, this means that if the potential is velocity dependent, you cannot write h equal to t plus v. All right, so if both these conditions are actually satisfied, then you can simply find the Hamiltonian by writing t plus v. This is very useful in competitive examinations, where we can save a lot of time by simply writing t plus v and then changing all the q dots in terms of p. Okay, so these 2 conditions, you have to check if these conditions are actually satisfied. If these conditions are satisfied, you can simply write t plus v and then get rid of all q dots in favor of p, and then you have got the Hamiltonian. Okay. Now, as a final note, we have discussed this relation between cyclic coordinates and conservation theorems in the Lagrangian. I hope you remember that. All right. So what do you mean by cyclic coordinate? It's a coordinate that does not appear explicitly in the Lagrangian. All right. So the conjugate momentum is then constant. All right. But we also know that pj dot is equal to dou L by dou qj. Okay. So if the Lagrangian does not involve any qj, if the Lagrangian does not involve some of the coordinates, then pj dot is 0, which means that you have got a conserved momentum. All right. But this pj dot is equal to minus dou h by dou qj. Okay. This pj dot is also equal to minus dou h by dou qj by what is a Hamilton's formalism. All right. So if the qj, if there is some coordinate that does not appear in the Hamiltonian also, the corresponding momentum is conserved. Alright, so just as in the Lagrangian, you can talk about cyclic coordinates in the case of Hamiltonian also. If some coordinate does not appear in the Hamiltonian, then the corresponding momentum, the momentum conjugate to that is conserved, is a conserved quantity. Okay, so the coordinate that's cyclic for the Lagrangian is also cyclic for Hamiltonian. If it does not appear in Lagrangian, it does not appear in the Hamiltonian. Okay. So if a generalized coordinate does not occur in H, the conjugate momentum is conserved. Okay, just like that. Alright, so the momentum conservation theorems can be transferred to the Hamiltonian formalism. So we have discussed this extensively in Lagrangian formalism. It's true, it holds true also in the Hamiltonian formalism. Alright, okay. So in the same way, the connection between invariance or symmetry and conservation can be derived from the Hamiltonian formalism. This is what we called as the Noether theorem. We have discussed it. It can also be derived in terms of the Hamiltonian. Okay. So we have conservation of linear and angular momentum corresponding to symmetries called translation symmetry and rotational symmetry. Okay. We have one more thing about conservation of energy. We had told that if the Lagrangian does not explicitly depend on time, then the energy of the system is actually conserved. It's true also here. So if you look at dH by dt, you can write as dou h by dou qi, qi dot, summation implied, okay, dou h by dou pi, pi dot, plus dou h by dou t. Okay. Now, so what we do here is that, so this dou h by dou qi is simply pi qi dot, okay. This dou h by dou pi is simply, dou h by dou qi is, what was dou h by dou qi? It's minus pi dot, okay. So this is minus pi dot qi dot, and dou h by dou pi is plus qi dot, okay. This is Hamilton's equation. So these two terms simply get cancelled. Okay, what we have is dH by dt equal to dou h by dou t, and we already found that dou h by dou t is minus dou L by dou t. Right? So if time does not appear explicitly in the Lagrangian, it will not be present in the Hamiltonian also, and then the Hamiltonian will be a constant in time. Okay. Now you have to be a bit careful here. We have discussed two things. The Hamiltonian can be total energy, and that total energy can be conserved. All right. The Hamiltonian need not be the total energy, and that Hamiltonian can be conserved. No problem. All right. So these things you have to be careful. So just because it's conserved doesn't mean that it's a total energy. If Hamiltonian has to be the total energy, it should satisfy a set of conditions that we discussed just in the previous slide. All right. And if the Hamiltonian is conserved, all right, it's just needed that the Hamiltonian does not explicitly depend on time. I'll just elaborate this. So if what we saw in the previous slide is that if the equations of transformation that define the generalized coordinates do not depend explicitly on time, okay, and if the potential is velocity independent, then Hamiltonian is the total energy. Fine. All right, but this Hamiltonian need not be conserved. This Hamiltonian still can have an explicit dependence on time. Okay, it need not be conserved. All right, so when you say that it's not conserved, we are talking only about part of a system. There may be some interaction with the environment, and then the energy of the system alone may not be conserved. All right, so the identification of H as a constant of the motion and as the total energy are two separate matters. Okay, you can identify H as the total energy, which need not be conserved. Okay, you can identify the so these are two separate things. All right, H can be conserved, but it need not be the total energy. All right, so just to make it more explicit, it is possible that the transformation equations involve time explicitly. Okay, and then Hamiltonian is not the total energy, but H does not. All right, it's possible that H does not involve time explicitly, then the Hamiltonian is conserved. All right, but it need not be the total energy. In this case, H is a constant of the motion, but it is not the total energy. Okay, so generally speaking, the Hamiltonian may not depend explicitly on time. Okay, and then it's a constant of motion. Fine. All right, but it need not be equal to T plus V. It need not be equal to the total energy or the sum of the kinetic and potential energies, either if the transformation equations involve time explicitly or if the potentials are velocity dependent. All right, so it means that H can be these are possibilities. It can be conserved and total energy. It can be the total energy. It can be the total energy and conserved at the same time. Okay, it's possible that it's not conserved. It's not conserved and it can be the total energy. Okay, it can be conserved. It can be conserved and not be the total energy. Okay, it can be conserved but not be the total energy. Okay, these possibilities are there, so you have to be a bit careful when we do such sort of things. Okay. All right. So with that, we have discussed the basic formalism of Hamiltonian mechanics. Okay. In the next session, immediately we'll start solving problems, and we'll be drawing on the concepts that we explained in this particular session. Okay. So with that, I'll conclude this. Please go through the slides. If you have any doubts, you can contact me. Okay. So I'll see you in the next session.